Okay, so I know not many people are going to watch this video because we're coming up really fast to the test, but this was a question that was highly missed on the multiple choice section of our mock exam. It was highly missed last year when I took my mock exam, and I know a lot of people on the review didn't get it. This example that I'm going to show you is of the day 2 of the review that we did. So you did get the answer key for it, but I know sometimes just looking at the answer key doesn't really help. I also know some people might not have opened the answer key, but that's beside the point. So this kind of question we talked about in period 2. Obviously I don't get a chance really to talk to the other classes, but in period 2 we talked about, as we were going over these multiple choice problems, looking at a problem and being able to identify what topic is this problem trying to get me to remember, right? Because that just puts you in a really good spot for knowing what direction you're going to go in. Or if it's something you have no idea how to do or you were really bad at, you might know, okay, I'm going to come back to that later if I have time, but I'm not going to waste my time on it, So let's start with this question. We're just going to read the information. Let's do orange, always. And I saw some people for their mock exams didn't have notes or didn't have extra scratch paper. You should always be taking notes, writing stuff down. You're going to need to on an AP Calculus test. And you're not getting extra points for not writing things down. You're not getting extra points for doing stuff in your head. If you're doing stuff in your head, you're probably doing it wrong. That was me. I never wanted to write anything down, but it's just like so much less confusing, and you're probably going to get the right answer more often if you're actually writing things down and thinking things out. Anyway, okay. An older sibling stands 12 feet from a little brother and watches a balloon tragically rising above the little brother. So rising, so we know it's moving. The balloon is rising at a constant rate, that's important, of 2 feet per second. What is the rate of change? So that's important, is knowing what the question's asking. What is the rate of change in radians per second of the angle theta at the instant when the balloon is 16 feet above the ground? So we're looking for the derivative, right? The rate of change of theta with respect to time, right? Because it's radians per second. That's a unit of time. And we're looking for it at the moment when the balloon is 16 feet above the ground. So we'll call the 16 feet h, right? The height above the ground. So when h equals 16. Right? So I think the big stumper of this problem is looking at this information, looking at this diagram and saying, like, what the heck am I doing? You know that you're, especially because this review is titled, you're working with derivatives, you're finding rate of change, so that also tells you you're working with derivatives, but like, what the heck? What's the function I'm finding the derivative of? What am I doing here? Because the topic that this relates to, we did not practice problems of that topic that looked like this, right? So the topic here is actually related rates, right? You can kind of get that from, it's giving us a rate and it's asking us about another rate. So those rates are probably related, right? So usually when we did related rates, we were looking at like change of rates where they were both side lengths. So maybe like, how does this distance change? What's the rate of change of that distance if the rate of change of this distance is a certain thing, right? But in this case, we're looking at the rate of change of an angle, right? But we can still relate a side length to an angle with a triangle, right? And so obviously the way we do that is with a trigonometric function, right? So first thing we're going to do, like we did in all of our other related rates problems, is write the equation that relates these two variables that we have the rate of change for one, we're trying to find the rate of change for another. So first we're just going to write the equation that relates them. So we know these people are 12 feet apart, right? And we're going to call that the distance between them, d, right? and that's constant, so that's never going to change. This height is changing, but we know the rate at which it's changing, and for now we're going to call that h still, right? So something we can do, if we know, we have definitions of these two sides. Here, let me get a different color, or I'll highlight. These two sides, which is this leg and this leg, right? It's a right triangle, obviously, because we have a distance and a height that are straight up from the ground. So if we want to know an angle and we have these two sides, the trigonometric function to relate them is tangent. So tangent of theta is equal to opposite, which is the height, over adjacent, which is d, or the distance between them. Already we can plug in d. We know d, right? Because d is a constant, which is 12. So I'm just going to do h times 1 over 12, right? Because I don't want to treat d as if it's a changing function, because it's never going to change, right? The reason I'm not substituting 16 for h is because that 16 is going to change as the balloon is rising. So it has a rate of change. So when I take the derivative of all of this, the implicit differentiation that we use when we're doing related rates, I want to have a dh dt in which I'm going to plug in this 2 feet per second that it's rising at. So that height is changing, so I'm not going to plug in a value for it yet, right? So now we can take the derivative with respect to time of both sides. So I'm going to take it of this side, tangent theta, and then I'm going to take it of this side, which I can actually take that 1/12 out front now, which just saves me some work, right? Like that. And again, so now we're treating the variables that we don't know as functions, right? So theta is not being treated as the independent variable, right? Because the independent variable that we're taking the derivative with respect to is t. So we have to use the chain rule here, actually, because it's as if this were its own function within tangent of x, but in this case x is theta, but theta is its own function because it is changing.